First of all, I would like you to imagine that you're a desk worker. The only thing he wants is board a marine facility from a small boat. As all of us, he wants to finish his workday to return home, spend time with friends. But the sea forces make the ship move abruptly, inducing a dangerous work environment. Now, let's scale it into offshore vessels with a whole crew on board, where it would be necessary even aerial rescues. Today, I'm presenting a possible solution to reduce one type of this movement and a technical methodology to do it: the design and simulation of a passive roll compensation system for offshore vessels. I'm sure this will be interesting for all of you. Allow me to introduce you to the dynamics of ship motions. Boats can move in 6 different ways: 3 translational and 3 rotational movements. Out of all of this, we're going to focus on the roll, because it's the main cause of the overturns on ships and a critical data for the operating limits of certain vessels. For example, in our study, a 140 meters crane ship was taken. Here, the roll is very important. Due to its long lever, a small movement on the main leg of the ship can cause considerable oscillations at the tip of the crane, which affect the forces and tensions with which the load is placed or lifted. Then, after all of the study and design recommendations, we can define an operating limit that, in this case, we'll use 2 degrees, where higher degrees of roll would make tension simply too strong and our crane could not work. The 2 degrees is a representative data and is used in the practice for big vessels according with other studies, which range a roll limit between 2 and 4 degrees. Now, the forces that the ship experiences, which produce all the type of movements previously mentioned, are the results of the wind forces plus the sea forces, which come to be their height and how frequent they crash on board. That, in technical words, are HS and TP. HS is the representative height in meters that gives the energetic level of the waves, and TP is the most recurrent period of these waves. These forces cannot be controlled, but they are known thanks for measurements for a long period of time, such as 10 or 20 years in a determined region, provided by well-known entities such as the National Oceanic and Atmospheric Administration, NOAA. So we made a mathematical model that simulates the behavior of the ship, having as a result the roll in function of time, allowing us to calculate its operability. That is nothing more than an average percentage of time in which a ship could work without exceeding its operating limits. Operability of 0% in certain months, such as January and February, making it useless, and just 20% in May and September. The problem lies right here. Where renting a huge crane vessel can cost more than $100,000 per day, and it takes almost 2 months for finishing a project that could have been done in a week if the crane had worked full time. That means savings of 80% in operation cost. According with this problem, a methodology and design of a passive roll compensation model are proposed. The model presented consists of a set of plates that will be transported folded alongside the boat in order to submerge and unfold them when the vessel remains static. It's a passive system because it does not require a supply of energy or a control for its operation. And how is the roll compensated? During the roll, the system causes the movement of all the mass of water that is on the plates. The water generates a force opposite to the movement, making it difficult for the boat to keep rolling. The more the boat wants to roll, the bigger the force against it. The ship has now more inertia, and the movement is reduced. The idea of using plates as a passive roll compensation system was based on this. Several designs and patents for small sailing boats, with not much study behind, but with good empirical results. Even a simple container, to a lesser extent, fulfilled the same principle to compensate the roll. Our design for offshore vessels is new, supported by a methodology, calculations, and simulations. So now the suggested solution is clear. We propose this methodology. First, the historical data of HS and TP was taken to generate an energy wave spectrum, which characterized the forces in a specific time. This was inserted in a dynamic system with geometric aspects of the crane ship study in order to solve the differential equation of the movement. This equation gives the dynamic behavior of the ship and plates presented by X, all with the help of the software ANSYS R1. where M and A are matrices of mass and momentum of inertia, in this case the ship and the plates. B is a matrix of absorption. K is a matrix of stiffness, and F represents external forces, including the Z forces. One of these dynamic responses is the roll, and it could be compared with the operational limit in order to get the monthly operability of the system. All the time the data is below the operational limits, the crane ship can work, but when it's above, the crane ship cannot. This is done several times to simulate the behavior of the ship with and without plates of different sizes and arrangements. In our case, 7 possible systems were proposed and analyzed, having the same tendency. The bigger the plate, the better the reduction of roll. That means an increase in operability. But we cannot just choose a huge plane to compensate all the roll. The selection part was based on the improvement in the operability of our boat with a roll compensation system, a construction cost analysis, and a feasibility study. Feasibility refers to the viability of the system implementation by answering questions such as, can the system be transported? Can it be built? Or does its weight influence considerably? With this logic, the smallest plates are discarded because its poor operability increase. The biggest plates are not so practical due to its weight and its size in relationship with the crane ship study. So between configuration 3 and 4, it's chosen the one with better operability. It consists of 4 plates of 28 by 14 meters, 2 on each side of the boat, with an estimated weight per plate of 812 tons. As next step, the chosen configuration is designed with all its details, having as a requirement robustness for its constant utilization and resistant to corrosion for its environment. The principal components are the beams of the structure that act as a main support, in this case type W, 2 hinges and 2 shock absorbing revers, known in the marine industry as fenders, which allow the system to open and fold, avoiding a rough contact between them. Leaf springs, which are smaller plates that work to fatigue, bending when receiving a force and then returning to its original position. These enhance stability and avoid loss of tension in the cables that hold the plates without using more hinges or moving parts. Concrete slabs. We simulate the chosen configuration varying the weight of the plates to find the minimum required weight, that the compensation system has to have in order to not lose tension in the cables, because it could produce a whip effect resulting in severe damages to the system. And finally, lifting hooks. The material selection for the beams, the springs, and the hinges was made considering the saltwater tested pack, where we can filter by common utilization of the material, in this case, offshore vessels, and different parameters such as excellent weldability, high corrosion resistance, minimum tensile yield strength, among others. To determine all the forces that are present on the plates, it shows its free body diagram for the 2 different directions of the movement. In this case, the left plate is trying to move up, while the right one is moving down. Notice that the drag force and the inertial force change their direction as a result of the change in the displacement direction. The gravity force and the buoyancy force remain constant, and the tension varies depending on the movement of the plates. The principal forces are the tension and the drag. The tension of the cables is a dynamic response of the simulation, and it's used to design the hooks. The drag force is used to design the beams, the leaf springs, and the hinges. It's calculated by the following common equation, where the density of the water and the superficial area are known. The velocity of the plate is other dynamic response of the simulation, and the drag coefficient, CD, is obtained through the Collegan-Carpenter coefficient, which is in function of the oscillation and the amplitude of the plates. In the experiment, they built and modeled a rectangular plates subjected to force oscillations, creating a graph that relates these 2 coefficients, CD and KC, without needing Reynolds in the equation. Also, a fatigue damage analysis is made for all the components of the plate. The process is Let the critical stress equation of the component as function of the principal force, like the tension or the drag. Then, with the historical forces in function of time and the stress equation of the component, generate an historical stress in function of time. This is inserted in a fatigue toolbox of MATLAB that works with the rainflow method, classifying the stresses in cycles. The damage is calculated for every cycle and it's added to obtain the total fatigue damage. Therefore, the design for all the components of the system could be adjusted in order to set their useful life to a specific period of time, or in order to have an approximated cost analysis for the implementation of the system. From a macro perspective, having an overview of the subject, our job not just present a technical methodology for the implementation and design for the passive role compensation system, but also great advantages in operability, security, and economy. For our case of study, the 140 meters crane ship in the North Sea, with the 2 degrees operating limit of roll, the reduction of roll allows the ship now navigate in waves 3 times higher in the same period TP, with the same stability below the 2 degrees of roll, which make it safer for unpredictable weather conditions like storms. The operability would triple, managing to work practically 5 months of the year above 30% in operability. And doing a simple economic analysis by taking a real project that lasted 80 days for the installation of the wind turbines, the following is obtained. The operating cost, which includes the daily cost of the ship, the number per trip, the cost per trip, among others, give a round total of $12 million. If this is increased by the manufacturing cost of our anti-roll plate system, which is not cheap, estimating a manufacturing cost per plate of $1.5 million, it's still totally worth it, because the total time in the development of the operation is reduced in relationship with the increase in the operability now obtained by the ship. It gives a round total cost of $11 million, having savings of 8% of the total cost of the operation in its first work, with all the investment return taking profits of 60% in future projects. Thus, demonstrating one feasibility case and a supported technical methodology for the implementation of the system, without even considering all the accidents that could be prevented with a more stable platform, or the infinite applications for a country that lives off marine trade like Ecuador. Thank you very much.
Me hubiera quedado loco estas últimas.